Awesome. Thanks, Andy, for hosting and for having me. My name is Drew. I'm the founder of Webb, and I'll be talking about the work we do at Webb. Specifically, these are some more high-level ideas, but relating to cross-chain zero-knowledge messaging and going into the things we build. Cool. If everyone can see, I'll get started. Awesome. Yeah. So, what are cross-chain zero-knowledge proofs, and why are we interested in them? First, we want to prove statements about one blockchain on another, and we might want to do this with some degree of privacy, or we might just want to compress a lot of information and make proofs about them on different blockchains. So the example in this diagram that you'll see is that we have a bridge between 4 different blockchains, and Alice can interact with smart contracts on any side of these chains. And the mechanism we want to enable is that she can go across chain and prove some knowledge of state on Ethereum as she's interacted down here. And she can do this with a zero knowledge proof. Potentially, she wants to prove that she owns some amount of tokens without disclosing, who or what account she owns, or something about her identity. The design space is quite open from this point. And why is it important? Why does it matter? Well, if we can do this with zero knowledge, then even as you make these proofs across chain, any observer won't be able to identify where these proofs are coming from, what their contents are, and you'll be able to do this now between different blockchains. So if many people are interacting from any different set of chains, no observer, Eve, will know, whether the person who's proving knowledge of some state is Bob or Alice. We tend to think of these things as users are putting messages into a bridge. They're inserting messages into Merkle trees or other cryptographic accumulators, and then they're using some augmented Merkle tree membership proof to prove that state exists in zero knowledge, without disclosing where that state is and sort of whatever contents they want to prove publicly and privately about them. Why are we interested in this? Well, the main thing at Webb, why we're interested in this, is ultimately to scale privacy, to create like the most scalable private sets and mechanisms. The things we're interested in are related primarily to identity and asset transfers. So we want to build large pools of identities or assets that people can move between. And we get a shared private primitive because we connect these systems together. And so, no matter where you're interacting from or where your data is being inserted from, you are contributing and leveraging privacy that everyone else in the set is creating. So the set is like, scaled across chains. And so it's effectively one set that people are creating privacy within. Other extensions that start to increase the complexity of what we've built already are to try and do this for arbitrary statements. So proving things about maybe a collection of virtual machines, rather than just proving something about a kind of restricted identity set or anonymity set. So the main mechanism we use to accomplish this is we connect cryptographic accumulators across chains. There's sort of 2 paradigms that we think about and are building more or less towards. The first one is where we customize messages and we customize our cryptographic accumulators to connect between different chains. We say this is easy because when you have full control over the hash function you're using and the contents of the message, then you can make a pretty application specific zero knowledge circuit to prove the statements you want. And the harder approach is to do this sort of with just the primitives that these blockchains natively provide. So trying to build circuits for multiple different environments that interact directly with like the Merkle-Patricia tree on Ethereum, for example. This is hard because if you were trying to build what Webb's built currently, say between Ethereum and Scroll, I'm slightly familiar that there are two different, they're using two different Merkle trees. Maybe there's a different encoding or some schema that's used differently. And so this becomes harder because now you'd have to build a circuit that is like proving that state is in one of these virtual machines underlying trees. So the circuit would be quite large, but I'm sure there's some aggregation or recursion you can leverage here. But yeah, so the basic primitive was, as we link these accumulators together, is to do a one of many membership proof. So take a bunch of Merkle trees, prove to me that you know some leaf in one of many of them. You don't tell me which Merkle tree this leaf is in, and you don't tell me, you know, the preimage of this leaf. And this is the basic mechanism, or not basic, but this is the mechanism that Webb uses for all of its applications. The one thing I just haven't discussed yet is how do we actually bridge these Merkle trees together? Specifically, how do we get the Merkle roots relayed to their peers, their neighboring points? So just to recap sort of like the two methods that I've described, when we connect these cryptographic accumulators, we can define our own accumulators, which come with their own messages. We'll hash them, insert them into these trees, and update this state across chain. Similar, you know, same thing, you do prove knowledge of some data in a set of roots. Or the generic method is like any interaction on this blockchain, I'll link their state trees together. And then I'll prove some more complicated statement. Like I'll prove that there's some state or some account that I own that has some state in this large tree. And it'll certainly be more complex, but that's the generic approach here. So this brings us to Webb's Tangle network. We're launching a blockchain as well. It serves a pretty much more narrower use case than any smart contract chain. But the intention is that this Tangle network will do the bridging and do the validation of like bridge updates, so that we can validate Merkle roots and send them to their neighbors. So this network right now, it's a threshold MPC-based governance system. So we're going to generate threshold signatures of the events that happen on any, you know, bridge of Webb. And we have a network of relayers that are going to relay to and from this chain the updates and these signatures. And the idea is that we can have some hybrid model where the goal is we're going to sign provably correct state updates with you know, an ECDSA signature, so it's really quick to verify and it's cheap to verify. And then we can take these signatures and update our bridge. Other, you know, similar ideas that I'm starting to see in the ecosystem are using aggregatable BLS signatures. You know, it's typical model for, you know, slightly distributing trust in a bridge that's not fully trustless yet. I say provably correct here because the way our governance system is being built right now is that the updates that can be proposed to be signed can only happen if they're proposed with the light client proof. So it's sort of like you can only propose things trustlessly, but then you trust the DKG to sign this update. Yeah, so this is the idea I just described. If a relayer can prove that some event happened with, say, a light client on our chain, then we hope that the underlying authorities and validators of the chain will sign it. So the types of updates that we are specifically focused on are, did the root of some Merkle tree on Ethereum or on Polkadot, did it change? And we sign that. And then we have some relayers who will relay the signatures, assuming that they are signed. I think this is quite nice, primarily because you can also bake in slashing conditions to this style of MPC. So specifically, since the rule of thumb we're trying to instill is that the DKG will only sign things that have a light client proof. So if they sign things without a light client proof, then we can use that as our slashing conditions. And I think we'll try to work on improving the trust model here to provide like stronger economic security over time, and explore, I think, as far trustless as we can get with zero knowledge bridges over time. But this is just an example diagram. You have these chains, relayers in between that are listening to events and relaying to and from the MPC. And so this is what it looks like, coming back to that main image. We have different users inserting messages into the bridge. We have these signatures being generated when messages are inserted. And when the state is updated around the system, these users can go anywhere and prove knowledge of these messages without disclosing who they are or where those messages come from, allowing us to build different types of applications. Yeah, so yeah.
Question for you. So what do you mean by prove knowledge of the message?
Yeah, so it's definitely depends on the type of application right now. But I could say proving knowledge of a message in the most simplistic case is just prove that the preimage of some leaf in one of many of these Merkle trees. That doesn't do much really, but
I see.
We'll
so that
see.
kind of,
Yeah.
it replaces the need for a signature on the other side of the bridge, essentially, for the signature.
Yeah, exactly.
All right.
So we're sort of accumulating these messages in Merkle trees and using our bridge signatures to just agree on the roots of those message sets. It sort of separates the responsibility of, what the bridge is really doing. The bridge is just sort of manipulating and moving around Merkle roots. It doesn't need to judge what the contents are. But yeah.
I see. So it's building the block, but then the block gets verified by the proving knowledge kind of aspect. Or not.
Yeah.
Verified, but yeah,
Kind of.
I see.
But yeah, any other questions? Now is a good time before we jump into specific, I'll say specific messages that we stick on these types of systems.
Are you guys using threshold cryptography like ECDSA or Schnorr, like GS22 or something?
Yeah, we are using GG20 threshold
GG20,
ECDSA right now. And yeah, the way it works right now, there's no resharing, but we do periodic rotations every 1 to 6 hours, where we'll regenerate a new key and we'll run some sort of rotation protocol that can be run by all the endpoints of a bridge as well. It's not like we want to improve this, of course, with some resharing, but trying to get to a live production network first.
Sweet.
Cool. Yeah.
I had a question. I hope people can hear me on the call, but Do you also have a concept of nullifiers? So like you prove a knowledge of some message in the tree, but you also have some invalidation so that you can only use it up once or something, some concept like that.
Yeah, so if anyone wasn't able to hear Andy's question, is dealing with nullifiers and nullifying like proving messages. The answer is yes. It's specific to applications that require you to like not be able to prove it again. So yes, basically.
Is it like built in?
It's built into the applications, really. It's not built in. So right now, every bridge that we've built is a bridge for a specific application as well. We haven't figured out how to generalize it entirely, but I'll have something to say about that at the end. Because yeah, there's different behaviors you might want of where things can be nullified and where things can't. Specifically, like the first types of applications that we've focused on are interoperable shielded pools. So like you can privately move an asset from one chain to another. In this example, your nullifier should only be your transaction should only be spendable in one place, because otherwise you might be able to double prove and withdraw in multiple places, which would be bad. So here we do have nullifiers and they're stored where these transactions are spendable. But yeah, why we're interested in these types of applications, well, you get an interoperable shielded pool that functions as a single anonymity set that users can now utilize and collaboratively contribute privacy towards without even needing to like care about using that chain or this chain, right? You can use these pools as, anonymity sets on your own chain, and you can use them as bridges. So it's sort of like in the spirit of people layering features on top of privacy systems, this is layering a bridge on top of one. Other examples are like Penumbra is layering swaps on top of one. So some type of action that additionally provides more privacy. Yeah, I'll leave it at that unless people have questions. I'm sure there might be, but so here's an example. Like our messages in this case are structured data that represent deposits. So I can deposit some amount of ETH on Ethereum or some amount of WETH on Polygon. And then we can go and withdraw a wrapped version of it across chain and potentially even unwrap it into some real underlying collateral if it exists. So the way we've architected the first version of this application is it can wrap multiple types of collaterals. So you can have, ETH, WETH, STETH, Coinbase ETH all sort of aggregated into a Webb ETH representation, and you can move this around and unwrap it if the liquidity exists. Like one small, way of describing this in the past was this would be a mechanism for supporting like a private cross-chain stable swap. So you could move between, similarly valued assets privately. The next types of applications that we've built are taking the semaphore mechanism and also turning it into this sort of bridge system. So now you can actually maintain a set of semaphore sets that all can prove some anonymous membership in the aggregate group. So there might be groups of NFT communities on the same chain and on different chains, and we all want to just prove that we're in this aggregate community. And you would still leverage, the same benefits as Semaphore. You'd be able to prove that you're in one group if you wanted to, maybe take some action or signal something, but you could also prove like without sharing which subgroup you're in. So we've built this. we haven't gotten to building any front end applications for it, but the mechanism exists, and we've been using this to inspire how composable and how composable some of the primitives that we're building are. Yeah, it's similar benefits. You know, I can say this, I can go on for hours, you know, just growing these anonymity sets across different locations or different communities just allows us to grow privacy larger, is the motivation. So here's a similar example. We have some identity issuer. We'll put the identities then in these Merkle trees. Those are our messages. They're like semaphore identity commitments. And then you prove membership across chain. In this case, you could prove, you know, we will nullify. So going back to your point, Andy, we will nullify these proofs, but you could, in the way this application is currently built, go to a different chain, also make a proof and like prove you're still a member, but with a different nullifier maybe, as long as it's different signal, different, or like, yeah, a different external nullifier. So there's a little bit of nuance here. We haven't fully thought of like, what is really the application in mind? But yeah. I think there was another slide I forgot to add. But the last note before I go into like some new work we've been working on is we've also combined our shielded pools and our semaphore protocol into an identity-based shielded pool. And this is where I think these tools start to be quite interesting to play around with, is like we could build a shielded pool where the only way you can transact is by continuously providing a proof that you're in this aggregate semaphore group. And then you're able to spend your shielded commitments and bridge assets across chain. And you continually have to prove membership in the semaphore set, which could be managed by some identity issuer who adds and removes people over time. So these primitives are all like, you can layer them on top of one another and build, you know, things collectively, which I think we're getting to like really nice architecture of. Yeah, go for it.
For that type of stuff to work, do you need one integrated system, or is it possible to implement that with like the semaphore system and then the shielded pool system?
So it's a separate semaphore system, and then we would deploy like this version of the shielded pools that point to those semaphore sets as their record of truth of like the identity set. So the identity set would need to exist on its own, you know,
as two separate Merkle trees.
Yeah, exactly. You'd have like a set of Merkle trees for your semaphore identity sets. And then you would say, okay, I'm going to create like commitment trees where the only people who can insert commitments for UTXOs into them must also be proving to me consistently that they have identities in this bridged identity set.
But that logic would like live in the smart contract, right?
Yeah. So these are like an augmented shielded pool we built. But yeah, they start to exist separately. So like if we succeed in building pretty large identity sets, anyone could come and say, yeah, let me hook into this, and I want my application to prove XYZ. The benefit being, you know, your users can register identities on some layer 2, and maybe then they can interact on layer 1 because it, you know, leverage what's cheap and what's efficient and so on. Yeah. And so in the spirit of, you know, continuing to increase complexity, we've been also now, like, these things are actually all built. We have tested them, and they exist today on our GitHub. We've been working on an increase in complexity to build multi-asset shielded pools that are interoperable with additional circuits to add new functionality. So now, like, this is the vision of for these types of applications. And again, we can maybe layer very seamlessly like an identity primitive on top, but we want to support multiple assets. So both fungible and non-fungible assets. And part of the functionality we wanted to provide in this MASP are to enable atomic swaps so that you could deposit an NFT. And while NFTs aren't special in shielded pools, I think they do become quite special when you can swap them for fungible assets in the shielded pool, because now the NFT can exchange owners privately. So that's functionality that we're definitely targeting in like this new version of the system or of an application, while also supporting the ability to like just move multiple types of assets between chains. So a slight increase in circuit complexity, as well as just having more circuits. But it's the same style mechanism, you know, the messages now just contain a little bit more data. Something else we're also improving here is to provide and build out like our first version of cross-chain incentives. So being able to prove that you did make a deposit on chain A, you might have spent it on chain B, trying to figure out how long were you in the pool for, but now doing it across chain, and supporting some other features like delegatable proof generation. This is just another example of the types of applications we're interested in building, and we hope to showcase to the world soon. But yeah, so what are we looking for in the future? I think Andy or someone may have asked this earlier, but we want to definitely generalize the system, and work towards that general approach that we talked about at the beginning, which is like, you know, well, I guess I'll start with point number one, but we want one set of linked accumulators for every message type. This could be solved in theory by like a completely general, like prove anything type of interface. It would certainly simplify the DevOps that we have to deal with. Right now, every application is a separate bridge. The MASP is certainly kind of building out in this spirit where we can have now one bridge for all assets. And the reason this is beneficial just on the DevOps side is it's fewer contracts to point to listen to relay events from, especially if we have nice large Merkle trees that store everything. One approach that is like loose in my head, if anyone knows more about this and wants to reach out, is kind of taking a page out of the ZKP book where you do just have arbitrary records with birth and death predicates, and maybe that's a way to build full generalization into the type of systems we're dealing with, where like you spend your records on the destination chain that you've specified, and you nullify it then and there, and you can't go and spend it on a different chain. So within this, I think those mechanisms require us to sort of augment our zero knowledge capabilities. We were still using Groth 16 and for most of our circuits, and maybe we have Plonk capabilities, but maybe there's, you know, the space is rapidly changing always, and so like maybe we'll figure out how to use Halo 2 or Plonky 2 here. Yeah, and some other things quite interested in at the end, like these sort of generalized state proofs across chain, similar to what E is building at Axiom for specific chains. Like we're certainly interested in exploring this as an idea where maybe you can prove any state you want, and this allows you to do things on top of the existing applications we've built. For example, like maybe instead of using Semaphore as your like whitelisting of, you know, your whitelisting system for a transaction system, maybe it's you also have to just give me this arbitrary general proof of some state, some account that you own, as a means of validating your ability to transact. So we're interested to kind of get to that stage as well. But yeah, that's what I've got. Happy to take questions, but here are some of our links to our GitHub documentation site and Twitter. Throw us a follow. Hope you enjoyed the talk. And yeah.
I've got a question.
Sure.
So you said like the multi-asset swaps will add complexity to your circuits. Could you just elaborate on like how your circuits depend on the particulars of the messages in the tree, and like,
so even before swaps, like for the mass, we're adding to our messages, we're adding like the asset identifier as now another parameter. In fact, we're adding like 2 asset identifiers because we want to support NFTs as well. And so we want to be able to like register an entire NFT collection instead of having to register like this token ID. So it makes our message have, let's say, 2 more fields, which takes us from like a Poseidon hash of a few things to a few plus 2 more things. And now our circuit just needs to reflect like reconstructing these messages in order to prove that they exist, but it'll need to do that in the circuit. In terms of the swap, we just have now another circuit. So like if you wanted to execute a swap, it's still touching the same Merkle trees. It's still leveraging the same structure of your records, but we have to build some new mechanism. It's not just spending it. It's, proving that a swap is somehow valid with, say, a signature that you are willing to sell me your NFT for 1 ETH.
okay, so the circuits are like particular to the asset you're operating on and the operation that you're doing on the asset.
Yeah.
It is like maybe a stupid question, but like, is there a way of like having a general message that's just like some encoding of something, or
Like a general circuit? Yeah.
Yeah, like do you have to structure it by asset type and operation, or is there like some more generalizable paradigm?
I imagine there's like the spectrum from this type of framework to all the way to like a zkEVM, right? So like I could look at everything as being a smart contract or a Zexy style system, and yeah, I think it should be possible. I have not entirely figured it out.
So like designing some like instruction set that encodes your operation that you want to do, and then building a circuit that proves that sort of instruction set.
For sure. Like I think there's definitely something to be said about how costly generalizing gets you. Like we want to run, we are running these applications right now in the browser. We're proving in the browser. So it's a question of like, if we generalize, like at what point does it push the computation outside of the browser? Because like now, you're doing you have some large circuit and it requires actually some sophisticated hardware. So I don't know, but if anyone has good ideas, they're like, I would love to chat. I think it's an area that I and our team certainly isn't right now focused on. In some sense, we see these as like, or at least, we see these as like building blocks, and we're trying to connect a bunch of Legos together because maybe someone can come along and build a new type of application specific to them. It's efficient. Our tools work well out of the box, but there's something to be said because everyone else is in this zero knowledge space is building like generalizable mechanisms, like just virtual machines. But So that's like a highlight of a lot of the applications we're building, and how the system works at large. Places we obviously will hope to improve on are also like doing more zero knowledge bridging as well, but yeah, we'll get to that in time. But cool, thanks for having me. I don't know if anyone else has questions, I'm happy to answer.
Yeah, anyone else got questions? I have some more questions.
Hit me.
Are like, is the infra, like the relayer stuff, is that all you're hosting that in a centralized way right now? And do you have a plan for like decentralization and incentives for that to become decentralized?
Our relayer today serves a variety of purposes. It like relays events. It also, for say the shielded pool application, there's like a portion of it that will relay transactions, like similar to, you know, previous privacy projects, Tornado Cash, etc. So that part, private transaction relaying, is like decentralized. You don't need to, like, you can run a relayer and charge fees to users who use your shielded pool. For the actual governance component, like relaying events to the bridge chain, right now it's semi-permission, but yeah, with light clients, it'll become fully permissionless. So like as a relayer, if I see an event, I just need to prove that that event happened against our light client, and then it'll automatically dispatch a proposal to be signed. So then anyone can run this service. And certainly there will be like, you know, if you're the guy who posted that light client proof, we'll pay you from the native token of that chain.
And you said that there's like a way of incentivizing through the shielded pool transaction. So that would be like built into specifically the shielded pool.
Yeah, exactly. So yeah,
You
exactly.
wouldn't be able to do that from like an identity set though.
If we would just have to customize that logic, I think. Like, but yeah, like I don't know, I could imagine if you consistently attest to an identity in a shielded pool, or like you consistently, I don't know, up its nonce, like the last time you maybe ran some identity check or proved the thing that let you create the identity, maybe you will get rewarded if you've done that so many times. But it's all sort of customizable to the circuit. So that's like where it's, I would say, the most friction comes from. It's like, yeah, right now it's very much like, do you know what application you want to build, what the properties of it are? If so, you can build it, make it cross-chain. The future is certainly like, can we get to a place where people can deploy these without having to run the whole infrastructure again?
It's like having a shared infrastructure layer.
Yeah, I feel like that is just the ZeX model, but built as a bridge. So yeah. There's that. There's also, I've heard like, however, Aztec's moving towards like user deployable smart contracts. Last sounded interesting, but patterns like that are how I would imagine you get to like being able to deploy everything under a single infrastructure.
All right, anyone else with questions before we wrap up?
Yes, I do have a question. I'm interested to learn about the performance, like you proved that gross 16 proof in the in a browser. So how many constraints and how long does it take for you to prove?
Yeah, I think right now our constraints are like, our circuits might be like 75,000 or 80,000 constraints. I know the MASP goes up to like 180 for the larger like 16 input to output join split circuit. And deposits take us, so deposits don't really require much upfront data. And we've seen that they take like 5 seconds to make, 5 to 10 seconds. The real bottleneck I don't think it's proof generation as much as it is gathering the witness data for making these proofs. So that's something tricky that we found in the browser environment, because you have to, potentially fetch data from multiple chains, fetch the state of those Merkle trees, rebuild them so that you have your witnesses.
That's very interesting. Just to clarify, so your prover is running in Wasm, or do you have a interface on the or Docker in your own local machine?
No, so we're using Snark.js right now. We used to have some things running in Wasm, but we're starting to try to converge specifically to one environment like Circom, and get, like, if we're building things in Rust, we'll use Arc Circom, or we're trying to get it working there. But just having one language for writing the circuits and doing the proving seemed to be better than trying to do things in Wasm.
Okay, cool. Thank you.
All right. So if there are no more questions, I think we can call it there. Thanks a lot, Drew. Appreciate it. That talk, that was great.
Cool, thanks for having me. Hope everyone enjoyed.
All right, see you, everybody.
Thank you.
Bye.
Have a good one.